Hello, future engineers. Welcome to my YouTube channel. This video will show or present solutions to three examples on general friction problems. If you are still new to my YouTube channel, don't forget to subscribe and press the notification bell if you want to be updated with my lecture videos, which will be intended to help civil engineering students and other allied engineering students to be successful in their chosen field. So I hope that you will enjoy watching and you can follow the solutions. So this is problem 4 of this series on friction. The 0.9 meter diameter cylinder weighs 1000 newtons. The coefficient of friction between the cylinder and both surfaces is 0.32. Determine the maximum magnitude of the counterclockwise couple M for which sliding will not occur. So this is the given figure. So let's have our solution here. Let's apply first the applied force, which is the weight of 1000 newtons. So the effect of this couple is to have a friction force to be upward to resist that um, impending motion, which is downward here and to the right here. So upward here, friction, and leftward here at the bottom. So let's call the normal reaction as N1, then friction upward, which is 0.32 of N1. At the bottom, let's call the normal force as N2 and friction to the left, 0.32 of N2. So from the figure, summation forces horizontal equals 0. So we have um, N2, summation forces vertical, sorry. So we have N2, then plus 0.32 of N1 minus 1000 equals 0. So N2 is equal to 1000 minus 0.32 of N1. Then summation forces X, N1 equals 0.32 of N2. So substituting the value of N2, which is 1000 minus 0.32 of N1, then we can now solve N1 equals 0.32 times 1000 divided by quantity 1 plus 0.32 squared. So N1 is equal to 290.28 newtons. Then N2 is 290.28 divided by 0.32. So N2 is 1000 minus 0.32 of N1 from this equation. So N2 is 907.11 newtons. Or you can solve N2 using this equation here because we have found N1. So summation moment about the center, all this vertical force and this N1 here will have no moment about the center O. So only the couple M, 0.32 of N1 and 0.32 of N2. Remember that the moment arm of these friction forces is the radius of the cylinder, which is 0.45 meters. So therefore, M is equal to 0.32 of N1, which is 290.28 times 0.45, plus 0.32 of N2, which is 907.11 times 0.45. So M is equal to 172.4 Newton meter counterclockwise. So that's the answer to this problem. So for problem 5, the masses of blocks A and B are 5 kilograms and 10 kilograms respectively. These blocks are interconnected by cords AC and BC. Knowing that the system is in equilibrium, determine part A, the friction force acting on each block. Then B, the minimum allowable coefficient of static friction between each block and its surface for static equilibrium. So here we go. The force in each block, we will call that mu S times A for block A and mu sub S B times NB for block B. So we have this force triangle. So 50 newtons. Then next is tension in BC, which makes an angle with a vertical of 20 because this is 70, 90 means 70 is 20. And tension in AC, which makes an angle with a vertical of this angle here is 70 degrees. So 70 degrees with the vertical. And therefore, this third angle opposite to 50 newtons is 90 degrees. So because it is 90, tension AC is 50 sine of 20, while tension BC is 50 sine of 70. So tension AC is 50 sine 20, 17.101. Tension BC, 50 sine 70 is equal to 46.985 newtons. So let's draw the free body diagram of block A. So we have 5 times 9.81, its weight, then tension, which is 17.101 newtons. Then we have the normal force NA and friction force, which is, I'll call it friction force, or mu A times NA. So summation forces horizontal equals 0, 17.101 cosine 20 degrees is minus NA equals 0, so NA is 16.07 newtons. Then, therefore, summation forces vertical, the friction force of body A should be equal to 5 times 9.81, then plus 17.101 sine of 20 degrees. So, plus 17.101 sine of 20 degrees. So, from there, this is the friction force. This should be the friction force of block A. Then, computing for the coefficient of friction, it should be greater than 3.416 newtons. Then, for block B, here is the free body diagram, 10 times 9.81 its weight, and the tension is 46.985, which makes an angle with horizontal of 70 degrees. And therefore, the normal at B, summation versus normal, is 10 times 9.81 plus 46.985 cosine of, sine of 70. So NB minus 10 times 9.81 minus 46.985 sine of 70 equals 0. So normal at B is 142.25 newtons. Then the friction at B is equal to mu S or mu B times NB, which is this component, horizontal component of tension, 46.985 cosine of 70. So mu B must be greater than 1. Mu B times NB should be greater, equal to 46.95 cosine 70. So this should be the friction force on block B, and therefore computing for the minimum coefficient of friction so that the body will be in equilibrium, or the entire system will be in static equilibrium, mu B is equal to 0.113 newtons. That's it. So problem 6. Three crates A, B, and C are placed on a ramp. Their weights are WA, WB equals 150 newtons. So WA and WB are each 150 newtons. W sub C is 225 newtons. The coefficient of static friction between the crates and the ramps are, so for under A and B, equal to 0.4 and under C, 0.2. Determine which, if any, of the crates will slide down the ramp. So this is the arrangement. So we should consider body C first. Let's draw the free body diagram. So this is body C, its weight is 225 newtons. Then let's have normal at body C. Then friction, which is equal to the maximum frictional resistance, is 0.2 of N sub C. Then we draw the normal axis. Remember that this angle is also 20 degrees. So the normal component is 225 cosine of 20. That is, so N sub C is 225 cosine 20 if you sum up forces normal, and this tangential component is 225 sine of 20. So if the difference, because this is the maximum frictional resistance under block C, if this point 2 of NC minus 225 sine of 20 is positive, then that means block C will remain at rest because the maximum frictional resistance is greater than this component of the weight along the tangential axis. If positive, the body will be at rest. If negative, then it will slide down the ramp. So N sub C is 225 cosine 20 degrees. Then let's call the net force as delta FC tangential, or delta T FT sub C, tangential C. So it is 0.2 of 225 cosine of 20, then minus 225 sine of 20. The result is negative. So therefore, block C will slide down. And remember that the force that will push B and A, or B in particular, will be this negative 34.67 newtons. So without this block C will just slide, and it will transmit this supposedly force C tends to push body B. So let's next analyze body B. Its weight is 150, and we have normal at B, maximum frictional resistance, which is 0.2 of NB, and normal axis. This normal component of weight is 150 cosine 20, and the tangential is 150 sine of 20. Then let's transmit the force. So NB is 150 cosine of 20. Then delta FTB is 0.4 times 150 cosine of 20 degrees minus 150 sine of 20 degrees, then minus this 34.64. So minus 34.64 because it is going down the ramp, parallel to the ramp, the plane of the ramp. So delta FT on B is negative 29.59. Again, this maximum frictional resistance is not enough to hold this block or crate B here. So crate B will also slide. And finally, block or crate A, the weight is also the same, 150. So normal at A is the same as 150 cosine of 20 degrees. So they are the same. Then this is 150 sine of 20. So let's evaluate delta FT sub A. So remember that B tends to push 29.59. So NA is 150 cosine 20, then delta FA is equal to 0.2 of NA, 150 cosine 20, minus 150 sine of 20, then minus 29.59. So delta T sub A is again negative 24.51 newtons, which means that crate A will slide also. So that to the question, determine which, if any, of the crates will slide down the ramp. So our answer is all crates will slide down the ramp. So that's it. And I hope that you were able to follow the solutions. These problems here are the basic problems on friction. So in my future videos, I will consider challenging problems for you to enjoy. So I hope you enjoy watching.